So I'm going to talk about running Netflix on Cassandra in the cloud, but I'm going to start off by just mentioning something for the locals, which is that Netflix announced a few months ago that we're coming to the Nordic countries in Q4, and it's October now, so it's Q4. So at some point in the relatively short future, you'll be able to get Netflix. And right now, if you go there, they just want to collect your email address. But I do want to highlight this quite nice little point down here. So if you look down here, it says EU West 1 DF69BE09C DK. That's an instance, Amazon instance running in Ireland, and it's figured out we're in Denmark. So anyway, that's just thought I'd highlight that. And hopefully there are local people who will sign up for this thing. So yesterday I gave a talk, and I went through a bunch of the stuff about Netflix and cloud and whatever, and I assumed that some of you would have been in that talk as well, so I'm not going to go over that much in great detail. The talk was videoed, you'll be able to find the slides anyway. I actually have a t-shirt that says blah blah cloud blah on it, but today I decided to be Chaos Monkey. Lots and lots of slides at slideshare.net/Netflix. This is one of the slides from yesterday, just to give a bit of context for people that weren't here yesterday. We have, over the last 3 years, basically moved all the different pieces of Netflix to the cloud, and all of the blue boxes on here are basically backed by Cassandra. Yeah, all of those, there's like a purple one that's MySQL. That one is in the process of being moved to Cassandra. And there's a bit of content management, and some of the stuff on that first column should actually be Cassandra as well nowadays. So I'm going to talk about Cassandra running on AWS, which for us is a highly available and durable deployment pattern, which looks something like this. What we have here is all of the client services that want to look up this particular piece of information. They all make REST calls to a service tier with a standard REST interface. That then is the only thing that talks to our Cassandra cluster. I think the one that I grabbed here is, I think there's 24 nodes here and probably about 50 here. And then some of these, there are like some of these little boxes have 500 machines. So these are distinct services, not distinct machines, right? So we have, I don't know, 300 different services, and some of them are backed. This middle tier REST service also synchronizes with the data center to post things back there for various reasons. When you're doing transitioning out of the data center, the data flow, like if the data center is your master, you can basically serve cache misses or look up stuff in the data center and pull it back in for the cloud. We now have the master copy of all our data running in the cloud, running in this Cassandra cluster, but we still post stuff back to the data center for some systems that aren't critical to the streaming service, but which we still need. And this diagram was done using AppDynamics, which you'll see pop up occasionally. So that's one Cassandra service. Think of it as like a materialized view would be for Oracle or MySQL. So this, for example, it's the subscriber service. The only thing I can do to the service is ask questions about the subscriber. I can give you a cookie or something, and it'll tell me which subscriber it is, that kind of thing. It doesn't do anything else. You can't join it. It's just a single purpose service. And a team owns that service, and an engineer built that service. And if it ever goes red and has bad response times, we know exactly who to call. And this Cassandra cluster serves only that one purpose, right? So we've partitioned everything out. So what that means is that in production, we actually have lots of these things. There's more than 50 distinct Cassandra clusters. They add up to more than 500 Cassandra nodes, various sizes. The smallest cluster we do are 6 nodes. The biggest we have is 72. Our daily backup volume, and that's compressed backups, is about 30 terabytes. So that's what we're backing up on a daily basis. And one of these clusters is doing over 250,000 writes per second and it's actually mostly logging data. We have quite a few high traffic clusters, and we have another cluster that has about 10 terabytes of data in it. So we have one very big cluster, one very high throughput cluster, and lots of stuff somewhere in between. So that's kind of where we've ended up. So I'm going to talk a bit about the rest of the architecture here. We get high availability by storing 3 copies of the data on the local instances on Cassandra. We use the local internal disks that are ephemeral, that go away if the machine dies. Okay? So we have 3 copies of that, and those 3 copies are in different data centers in different buildings. In fact, the writes go to RAM, and then it acts back and says, that's fine, you're done. You can get a fast write by saying, let me know when one of the Cassandra nodes is completed. You can get a durable write by doing a 2 out of 3 quorum write and a 2 out of 3 quorum read after, if you want to get read after write consistency. These availability zones are separate buildings, separate power. I'm not sure how far apart, but they're a few miles apart, and they are about a millisecond apart, which means that if you want to get a fast request, you talk to the Cassandra node that's in the same building as you, because the clients are also spread across these 3 zones, right? So think of 3 different buildings. If you're in one building, there is a Cassandra cluster node in your building that has a copy of your data. If you want consistency, you have to talk to one of the other buildings as well to make sure everyone has the right data. So we triple replicate. We take our little map of all the services talking to each other, and we have 3 copies of it in 3 different buildings. And then we have Cassandra backend replicas, and Cassandra is doing the side-to-side replication that basically keeps everything in sync. So if you write some data, it gets copied sideways. And then the load balancers send the traffic into the top. If we're doing maintenance on Cassandra, which we do for upgrading the version of Cassandra or doing repairs or compaction sometimes, depending on what we'll talk later about why we do that. We take a particular Cassandra instance out of service. Now that means that I only have 2 copies of that particular data. I mean, this is a part of the data for this tier. One Cassandra instance comes out of service. What I do is stop replicating to it, and then all the machines that are in this cluster, in this availability zone, talk to Cassandra in the other zones. So that's normal operation. We're doing that continuously. We have Jenkins jobs that continuously walk around our Cassandra clusters, running repairs and compactions and doing software updates for new versions of Cassandra. So that's rolling continuously. So the individual nodes, I'm going to look at how we set them up. So we have a base AMI. It's currently CentOS. We're gradually moving towards Ubuntu, but we've been spending most of this year doing that, and we haven't got there yet. It's a fairly low priority job because CentOS basically works. We run a mixture of Java 6 and Java 7. The Cassandra clusters mostly run 7 now. Within the main JVM, we have Cassandra 1.09 currently. We're just moving to 1.1. There's an app agent monitoring it, which instruments the Java bytecodes here, and we have some garbage and thread dump logging. On the side here, outside the main Java virtual machine, we have monitoring, log rotation, a machine agent that's telling us how busy Linux is, things like that. And we have this service here called Priam, which is our Cassandra management process. That's running in a Tomcat server, which is our standard for our platform. Every instance we have, basically, almost every instance runs a Tomcat server. Normally, we deploy code into Tomcat, and that would be the main JVM on the machine, consuming most of the RAM. For our Cassandra nodes, it's a little different because we run Cassandra in a separate JVM that consumes most of the RAM. Well, actually, let's say this is a 68 gigabyte machine. We run Cassandra in about 6 or 7 gigabyte heap. Priam and these other things are probably using a gigabyte, and the rest of memory is file system cache. So that's roughly how we configure it. So Priam is available on GitHub. This is the secret source, or it's not secret, I guess public source, which we now have for doing zero-touch order configuration of our Cassandra cluster. So for me to provision a Cassandra cluster, I just have to say, please make 24 nodes. Those 24 nodes will self-organize into a 24-node Cassandra cluster, and from me deciding to do it, to have a running cluster that I can write to, takes about 5 minutes. 5 minutes, okay? And 3 of those minutes is Amazon creating the instances and booting them up, and then there's like a minute or two of Priam starting. You got to start Tomcat, and then it's got to decide what to do, configure things, and start the Cassandra nodes themselves. So what that's doing is figuring out what the Cassandra configuration files should have in them, figuring out, is this new, I'm a new Cassandra node, I just came into existence. Am I joining an existing cluster? Should I be repairing that cluster because I'm replacing a broken node? That's one case. If I'm a brand new cluster, I set up as an empty system, or I can actually also do a restore from backup. And you just tell it what time you want to restore from, and it pulls all data up to that point in time. So it's doing token allocation, assignment, I've talked about this. So the other thing that Priam does is continuously archive into S3. All the data that's written into Cassandra is logged to disk as large immutable files. Whenever one of those files is written, we copy that data into S3 and we compress it as it goes. And then we can restore that from S3. Finally, you can also grow and shrink the ring. You can tell it to double or halve currently, and I'll talk more about that later. And those are all functions which are implemented with Priam. Priam also has some monitoring interfaces. Think of this as a REST-based user interface to Cassandra on a per-node basis. We have a client library that we've also written, it's also open source, called Astyanax. All this stuff's on GitHub. This is an improvement of the previous Java client library, which is called Hector. Obviously, we're all very familiar with Greek mythology. It's part now of the interview questions at Netflix. So Cassandra was a woman in Greek mythology. Hector was her boyfriend. And Astyanax was the son of Hector, but not actually Cassandra's son, I think. I'm not sure. And later on, we'll run into some more Greek characters. So Astyanax has a much better abstraction and is for the RPC protocol handling and the thread handling. Has a nice Fluent style API. I'll show you an example on the next slide. It has a much better retry and back-off semantics, and it's also token-aware, and I'll explain what that means. With Astyanax comes a bunch of useful recipes because our developers keep doing stuff and keep asking the same questions. So we've built standard recipes for things like distributed row lock, which you can do with Zookeeper, but we figured out how to do it without. Multi-datacenter row lock, uniqueness, multi-yo constraints, and then this large file storage. If you want to store like 10 gigabyte chunks into Cassandra, which seems like a reasonable thing to do, I guess, then the problem is that if it fails near the end of writing a 10 gigabyte chunk, you have to write the whole chunk again. So what we have is a chunked and threaded thing which breaks your large write into lots of little writes, and they can all be individually retried, and that's a standard feature of the Astyanax client. This is what a query example looks like. We're not using any SQL-like language where you're sitting there cutting and pasting strings together to create a query. We just create it directly. You can see it's this Fluent style thing.thing.thing.thing. So this basically says, here's my query, it's preparing the query, get the key, I want to paginate it. You set it all up, and then you just sear it, get the result. Zip through, you're done, right? So it's nice, easy Java level API. So let's look at what Cassandra write flows look like. We've got the clients in the middle. They pick a Cassandra, this is a 6-node Cassandra cluster with triple replication. So I've got two red nodes in zone B, 2 yellow nodes in zone A, and 2 blue nodes in zone C. Okay? And the clients from whichever zone they're in pick a node at random, send it a request. There's a fairly small chance that the machine, well, in fact, in this case, there's a 50% chance that that node contains the data you asked for, but the client has no idea. Whereas the cluster gets bigger, the probability you hit the right node reduces. That node acts as a coordinator, figures out where the data lives, talks to the other 3 nodes, writes the data to all of them, and you can see the sequence I sort of walked through here. The key thing is that you get an ACK as soon as you're in memory on the other nodes, and about 10 seconds later it gets flushed to disk. And you could say, well, that's not fully durable, but I have 3 different buildings that I have data in memory. And if I lose a building, I still have 2 more copies in memory. It's quite hard to take out 3 buildings within a 10-second period without having a problem that's big enough that you no longer care about whether Cassandra is running or not. You know, if you drop an atom bomb on the east side of the US, the last thing you care about is whether Netflix is still running. Right. So what Astyanax does is that the client goes and pulls a describe ring every now and again and knows what the token ranges for each client are. And what it can do is say, well, this data I know is in the red node here, and it's not in this red node here. So I'm going to go directly to that one, and then that will also coordinate the other 2 copies. But what it means is that if you're trying to do a read one or a write one, which is the fastest request type, in this case, I actually have 2 hops to get to my data. There's 2 network hops, which, you know, every time you go across the network, there's delay. So it means that there's less latency and there's less that can go wrong. Every time you go across the network, it could also fail. So by having a single network operation, we reduce our latency. So all of this gives us an improvement over the previous Hector library that gives us more resilience and lower latency. Now, we run Cassandra in multi-region mode, and in that case, we have a cluster in Europe and a cluster in the US. So this is running in Amazon Ireland. This is running in Amazon East Coast. So here's a US client writing some data. This is the previous diagram, but the coordinator this time knows it's got a bunch of buddies in Europe, so it sends 1 copy of the data to Europe. That coordinator in Europe makes the other 2 copies, and then those 2 nodes ACK back to this coordinator, and you finally get an ACK. The ACK happens early for these clients. It happens as soon as it's consistent locally. The remote coordinator holds a copy of the data until it's heard from the remote cluster. So this copy is not delaying the write, but it's making it resilient to downtime. So it's just called hinted handoff, and it basically sits there and says, until I've heard that you've got the data, I'm going to keep a copy of it. And once I hear from everyone they've got it, I can drop that. So what that means is the overhead of having another remote cluster is a little bit of extra memory, thread handling, and traffic here, but there's no latency overhead to the local cluster. And that applies symmetrically. So if you sign up in Europe in a few weeks' time, whenever it is that we have Denmark support, you will enter your data, we will log you as a local customer here, your data will then move back to the US, and then if you happen to visit the US 1 second later, for example, because you have a very fast aircraft or something, you'll find you're a customer in the US. We recognize you. Every member of Netflix is a global member of Netflix. It doesn't matter where you sign up. You get local content for whatever content we've licensed in the US or the UK or whatever. It depends what country you're in. But it is a global membership model. When we were booting this up, we had the US region running with Cassandra, and with no downtime at all, we set up the European cluster and linked everything together. So to get there, we actually took backups and copied the backups to Europe and did a restore here. So this was mostly up to date, but a little bit running behind. Then we did a global repair to get everything back in sync. What that meant was it was a little faster and it put a little less traffic on the US to go from a backup. But we could, if it's a small cluster with a small amount of data in it, we just do a sync. This particular thing was for clusters that had a lot of data. We actually used a backup to try and just accelerate the thing. So let's talk a bit more about the backups. Oh, I like my analogy here, by the way. This is like taking a 737 on a domestic flight, and while it's flying, strapping on some more engines and bigger fuel tanks and flying it to Europe, okay, without landing it. And that worked out pretty well. We've done this we have approximately 10 or 15 clusters that are globally run in a global mode. Okay, for backups, we have, let's see, These are all the nodes. What they do is they have they're configured with an Amazon S3 bucket, and whenever they write to disk, they write an immutable SS table file, which was described in the previous talk. And that SS table is compressed using snappy compression, which is nice low overhead method, gives you a reasonable amount of compression, and is copied to S3. That happens incrementally as everything writes, and we do a daily full dump where we clear out the incrementals afterwards, but we've got then a full snapshot. So we have a daily full and an incremental every time you write an SS table. Once a day, we also take a copy of everything that's there and copy it to the other side of the country in a different region with a different Amazon account, and we encrypt it and all that kind of stuff because you get paranoid, and this is business protection, basically. This is the master copy of Netflix's customer database. I don't want to lose it, okay. And I probably don't want you to steal it. So we have a lot of these clusters. We're going to be open sourcing this soon, but we built a Cassandra Explorer, and you can see this is an old list of some of the clusters that we have. We just have an endless number of them. So why do we have so many clusters? Because we made it really easy for developers in a few minutes to create their own cluster, and we encourage developers to have their own cluster that they access that doesn't get in anyone else's way, there's no one else sending traffic to it. So its separation of concerns makes everything very identifiable. So the problem with that is you end up with too many clusters to monitor. And what we built was our own tooling that gives you a list of clusters. You can go in and you can look at the schemas and key spaces. This is a sandbox with a bunch of test stuff in it, running in our test account. So the Explorers is based on a framework. It's I think the client side. It's mostly based on Groovy, Grail's backend, and I think it's D3 is the front-end GUI stuff. So there's a bunch of basic Explorer technologies we've used in many cases to build these kinds of dashboards for managing stuff, and that framework should be out in the next few months. So another problem we have is, because we've got so many Cassandra clusters, is ETL. Normally, you go to your big Oracle or MySQL backend that's got all your tables in, and you suck everything out, and you do your integration queries, and then you spit everything into business intelligence. But the trouble is we've denormalized our data set across a huge number of clusters, and there is no place where you can do a join. And in some cases, we're logging data directly for business intelligence, but in some cases, they just want everything. Like they want the entire membership database to cross-link with everything else. The more event stream stuff they'll take as a log, but sometimes some of the things they need is the complete set. So we built a Hadoop input formatter that reads Cassandra SS tables. There is no actual Cassandra running, but it consumes the backups. And this is called Aegisthus. Aegisthus in Greek mythology is the person that killed Cassandra, because there is no actual Cassandra here. A dead cluster is imported by Aegisthus, and we basically, in bulk, we have a continuously running single Hadoop job, a Hadoop cluster, which sucks in large amounts of Cassandra, does the joins and the ETL and all that stuff, and then sticks it into our backend Teradata. We have a little Teradata. It's not getting any bigger. We're surrounding it by more and more Hadoop. And the master copy of our business intelligence software is now moving from being the Teradata version, which no longer has room to hold it, to being in Hadoop, and that's all running. The Hadoop is all running as Amazon EMR in the cloud. So I've been talking about the user interface for running this, and I'll show you what the screenshots look like later. But our web-based cloud management tool is called Asgard. We got fed up with, well, the team that was doing Greek god names, there's a different team, and they decided to do Norse gods for the hell of it. So we have Asgard, which is where the gods that manage the clouds live, I think, something like that. There's probably much better experts on Norse mythology here than me. Groovy Grail's JVM-based, supports Amazon regions. It's very specific to the AWS feature set. It goes very deep. But the key thing we built was to hide the AWS credentials, to have one copy of Asgard per account. And so we have a separate portal, basically, for managing test and production and things like that. So the projects that we have, the red ones here are things that are currently on GitHub. The blue one, this is Cassandra, which is already out there, but we've checked in a lot of code into Cassandra specifically for managing. We're a major contributor to Cassandra, basically, particularly for EC2 support. This is currently a blog post that we haven't had anyone actually ask us to open source it yet. And then we have these two, which have been described in blog posts, but we're now planning to release them as open source things on GitHub. Circuit breaker is the release it pattern. If you've been listening to Michael Nygaard's talks and a lot of other talks, been talking about circuit breaker patterns. This is a Java implementation of that we'll be releasing soon. So let me see. Priam, these two I talked about. Jmeter is a load test suite we use for checking out benchmarking and testing new versions of Cassandra. I'll show you that again a little bit later. We use Zookeeper for distributed coordination, so we have Zookeeper patterns. That's called Curator. That's probably the most popular project we have. It's got nothing to do with cloud. If you're using Zookeeper, you probably want to be using Curator. Exhibitor is like Priam, but for keeping Zookeepers running in the cloud and doing backups and things like that. Let's see. We have a service directory called Eureka, which we also internally call the discovery service. We have a dynamic property service we call Archaeus, which is actually it's a kind of a gecko. It's some lizardy thing. It's got nothing to do with Greek mythology, although it sounds like it should. Auto-scaling scripts and things, Asgard, and the Chaos Monkey. I'm wearing the shirt, obviously, but this thing is a robustness verification. If you look at the Chaos Monkey code, it looks overly complicated for what it does. The reason is it's a framework for supporting about 10 different varieties of monkey that are all specialized for different tasks. And the two that we're currently working on are Latency Monkey and Janitor Monkey. Latency Monkey doesn't go around killing things, it goes around doing latency and error injection. So instead of killing a service, it causes the service to return an arbitrary error code or to delay the response at some random frequency. That has been extremely useful for finding all kinds of interesting bugs. Janitor Monkey cleans up unused resources. It notices that you have an autoscale group that's not been touched for a week or so, and it's sort of harvesting things. They both use a database which we've internally called entry points for obscure reasons. Think of collecting everything about your infrastructure. You walk through the Amazon instances that you have, and you do describe instance on everything that's there. You can enumerate everything in your infrastructure. This means you can make strong assertions about your infrastructure, which is a very interesting concept for security, but that's not really the subject of this talk. Entry points is where we log that data. So entry points is walking the describe calls against all the AWS entities. It's also talking to Eureka and pulling our service directory and pulling all of our describe data and a few other things, and it builds a complete view of the world. But the interesting thing is, it doesn't throw it away. It remembers the differences. So now I can get the view of what my Amazon environment looked like a week ago. And I can difference that to now and see what changed, which is how the Janitor Monkey works. It's how it knows that you didn't touch this thing for a week, because it can see the state of it hasn't changed. And we can do interesting things now because we have a view into history. So again, that service is coming out. It's basically a big pile of JSON objects that are being indexed in interesting ways. And the fairly obvious implementation of that is to use MongoDB, because that's kind of what MongoDB is. So that's, it's a big JSON integration, slice and dice thing. Explorer, as I mentioned, I showed you. We're rebuilding all of our internal code using Juice as dependency injection framework. That's going to come out soon. It's called Governator is the name of the library. It's like an extended version of Juice. Odin is coming from the same team that did Asgard, as you may be able to guess, which is doing workflow orchestration. There's logging, latency injection, bits and pieces here. Oh, the Dynaslaves, this is part of the build system. So we have a bakery, which is how we build our AMIs. Dynaslave is a way to cloud burst your Jenkins system that's sitting in your build system, your continuous integration build system sitting in the data center, but every now and again you have to do a big build and it takes too long. So what Dynaslave does is create build slaves in the cloud as part of an Amazon VPC extension of your data center to handle the burst, and then they disappear again and fall back to your data center-based sort of baseline. So that's basically it. Okay, so that's most of the architectural stuff. Now I'm going to talk about some benchmarks and scalability. Some point about a year ago, almost a year ago, we ran some scalability benchmarks. So we took the version of Prius that we had at the time, we took the version of Cassandra that we had at the time, with the biggest cluster we were running was sort of 24 to 48 nodes. We were just firing up 48 nodes. And I said, well, what happens when you scale and get a bigger and bigger Cassandra cluster? And how far can you take it? And I said, well, let's keep going until we get a big number. And I decided that 1 million writes a second was a big number. So we did that. And DataStax started advertising that you could do 1 million writes per second in the cloud. I mean, I was getting pop-up ads for my benchmark. If you click through DataStax's site, you ended up on the Netflix blog site. So that was cool. It turns out that the universal unit of marketing is 1 million. Whatever you're doing, scale it so it was 1 million of, right? Units of per second, per hour, per day. If you say it's 1 billion, it sounds like you're trying too hard. And if it's only 1,000, it's not impressive, right? I mean, even if it's 1,000 per microsecond and 1 billion per month and 1 million, right? So you want to pick 1 million. And this is I did 48, 96, 144, and then we just went for it and did 288 nodes. These are running fairly small nodes because I was trying scalability. I wasn't going for vertical, I was going for horizontal. So yeah, you could do 1 million writes per second with a lot fewer nodes, but I wanted to see, was it linear? And this is pretty much as a straight line as you'll see on a scalability graph. And we got bored at this point. I mean, I don't know, it probably goes up here somewhere, right? Thousands of nodes, it sounds plausible. The individual nodes were about as busy at this point as they were at this point. So the overhead of adding more capacity goes up. This is for 100% writes. Now, reads is a different story, but particularly, Cassandra's always been good at writes. It's getting better at reads. So that's the best way of thinking about it. This benchmark was run in about an hour. I only needed 288 machines for an hour, cost a few $100s, gave it all back, we're done, right? This is the beauty of benchmarking in the cloud. So the next benchmark we did was more recent, and we've been looking at this for a while, and where is the future? Where are we going in terms of cloud and storage? And we'd been twisting Amazon's arms for a while over solid-state disks. So what we've been running on, mostly to now, is these machines. They're M2 4X large, they have 68 gig of RAM, a 1 gig network. You can do maybe 500 IOPS, there's 2 internal disks. You can get about 100 megabytes per second on the disks, and yeah, they're kind of relatively expensive, but you get a decent amount of memory and a reasonable amount of, this is the CPU. So what they came out with was these SSD-based instances. So you get 2 terabytes of built-in SSD. They're stripes of smaller SSDs. It's got a bit more CPU power, about the same RAM, 10 gig network, 100,000 IOPS, and a gigabyte a second to disk, and a gigabyte per second on the network. So it's a balanced throughput gigabyte per second server that you can do 100,000 IOPS at. And we're, okay, give us hundreds of those and we'll move all our Cassandra cluster to it. So that was the general idea. So we posted a benchmark. We did a load test driver. We had the same REST application service. And this is what we're currently running. We're running 36 M2 extra large Memcached because Cassandra's not always that good at read performance. And then we have 48 M4 extra large Cassandras to have enough I/O bandwidth to handle the reads and writes. This is handling the bookmarks. Well, everybody that ever watches a movie, it remembers where you are in that movie. And that's updated once a minute. So there's a large amount of traffic on this, read and write. What we benchmarked it against was a much smaller cluster of Cassandra nodes with no memcache in between and the same service hitting it. So this is the comparison that was approximately equivalent. And since there's so many fewer of these and we don't need any mem caches to get good read performance, it worked out about half the cost. So we currently have about 100 SSD instances that Amazon has finally given us that we can put into production. They are pretty rare right now. It's a bit easier to get them in the European clusters, but this is kind of the future. This is a system that has an excess of I/O capacity, and it always used to be that in the cloud you didn't have enough I/O capacity. So there's a bunch of things that we don't do. This is a slide I used yesterday, but it's one of my favorite slides, right? Particularly when we're benchmarking. But one of the things we do, and this is going back to the Cassandra Summit a few months ago, I ran a benchmark live on stage just to show what it's really like to run Cassandra. But I'm just going to rerun the results of that. I'm not actually going to run it live. And this is what I actually put up. It says, OK, I'm about to start this benchmark. And YOLO means you only live once. This happened a week after another event. This is an event that redefined the meaning of the word hard for an engineering project. Remember what that project was? What happened this summer that sounded like, that's hard. It's kind of hard. Let's just land a truck on Mars from a sky crane. That's hard. What I'm doing isn't hard. That's hard, right? So that was my okay. If they can land a sky crane on Mars, I can do a live demo. That was my attitude. There was a guy from JPL in the audience who liked that slide, so that was cool too. So we have a Jenkins automation. We have the Jmeter code that we put up. We have a Jenkins wrapper around it. The traffic was reading and writing 100-column rows. We have 25 million row keys, which is our sort of customer base sized benchmark. We ran it for 10 minutes and then doubled the size of the cluster. So it takes me 5 minutes to create this cluster, I run traffic into it for 10 minutes, and then I tell it to double the size, and I run it for another 10 minutes, wrap up the whole thing in about 30, 40 minutes, and I'm done. So let's see if I can get through this. First thing, this is Asgard. Before I start running, ignore the one in the middle, I have an M2 test and a SSD test. The M2 is the non-SSD one. And I have no instances and no autoscale groups, and Dennis set this up for me. Here's my Jenkins. I have 2 build scripts, and I've checked it. I tested it a few times to see if it worked, and Dennis built this stuff for me and debugged it. So this is the build parameters. When you hit run, you get to look at all this stuff. I won't go through it in detail. This is basically controlling how many Jmeter drivers we need. So it's a build job that creates a benchmark, and it creates the Jmeter drivers, and then the output of the build job is the graphs that show what happened during the benchmark, right? So the output of the build is a bunch of plots, and the machines no longer exist. They gave them back again. So it just runs to completion. So after running it a bit, here we have 3 ASGs, 1 per zone. We have 12 instances. I've got 2 12-node clusters. This is another one of our Cassandra monitoring Explorer things. It's called Kyklos, which is Greek for circles. And I had 12 nodes running, and then as we were scaling it up, you could see the nodes appearing. This thing was updating every few seconds, and it was showing the new nodes coming in. So the red ones are ones where Cassandra is not yet running, but it's declared that Priam has basically grabbed a token. There's one going to be here. It's grabbed a slot. This is bootstrapping, pulling in the data. The green ones are in service. And when they garbage collect, it basically goes yellow, so you can see if you've got too much garbage collecting going on. A little bit later, this one, for some reason, had finished a little earlier. This one was coming up. And if you mouse over something, you can see how much data it has on it and what else is going on. There's a bunch of other things. So out of this whole talk, when we gave it last time, everyone just wanted this tool, it turns out. Okay, so and it's coming soon. So this is what happened. It was a 1-hour talk. This was where I kicked off the machines. And this is how busy the machines were. And this is the CPU, this is the network, and this is the IOPS. So you can see here, we couldn't really drive the M2 to 4x larges above 500 IOPS, but the SSDs were up at 3,000 IOPS at peak. So this is the initial running of the benchmark. This is the auto-scaling, scaling it up, and then this was, I guess, doing the resyncs and things. Okay, and this is the output of the build, which is a whole lot of graphs. This is one of the graphs, which shows how many instances there were per availability zone. So I have 4, and it ended up at 8, which is good. And here's the read latency the read latency between the two. So this is in microseconds. So this is half a millisecond. So you can see that the read latency for the SSD instance stayed under a millisecond in the whole time. It sort of ramped up as we sent more traffic to it, but it stayed pretty flat. The read latency for the one using regular disks was about 50 milliseconds at peak, and basically, it was happy until we tried autoscaling. It's a pretty nasty thing to do, to autoscale a Cassandra cluster, because you have to shuffle all the data around. So the next steps. We're migrating our production Cassandra to solid-state disks. Several clusters have done about 100 running. The next step from a code point of view is to take Priam and start auto-scaling Cassandra. In 1.2, Cassandra has vnodes. Basically, right now, the only sensible way of scaling Cassandra is to double or halve the size of the ring, so that each node splits to a buddy or coalesces 2 to 1. vnodes is an extra level of indirection in the token mapping that lets you add one node and move just some data to it without affecting too much of the rest of the system. It's part of the original Dynamo paper. It's something that React already has. So it's not new technology. It's something that was just missing from the original implementation of Cassandra. So with vnodes, we can start adding and shrinking our cluster by one node at a time. And what we'll end up with is a cluster where you just launch it. When you start writing data to it, we'll say, let's have no more than 100 gigabytes or 500 gigabytes of data per node. And once it fills to that point, it will just start growing, because capacity growth. So you never run out of disk space. Your cluster just gets bigger. And then as you send it traffic, it will grow to the level of traffic additionally, right? So if you send it enough traffic, it will end up having half the data. So if you send it twice the traffic. Now every night at 4 a.m. we need we'd probably need much smaller clusters than we would at 7 p.m. So what we can do is have our Cassandra clusters auto-scaling and growing and shrinking every night. And one way of thinking about this is historically a lot of the advances in technology come by learning how to waste something. Some resource that used to be really, really difficult to find and was constrained suddenly becomes abundant. And here, IOPS were a constraint. Now they're abundant. So what I'm doing is figuring out, how can I waste IOPS? I'm wasting IOPS here in order to save something else. And what I can do here is waste IOPS by autoscaling a back-end stateful server and save on money by having fewer instances, and also make the whole automation better. So there's going to be some, SSDs are game changers and there's going to be new applications, new things that you couldn't do before. Okay, so I've got a few minutes left, and I'm going to talk about a Netflix internal hack day project, which luckily was not actually implemented. It's Skynet. Okay, so Skynet is the computer from the Terminator movies, and luckily it's only been implemented in PowerPoint, but I figured out how to implement Skynet in Cassandra. So those of you that don't know what I'm talking about, the bits of the plot that matter is Skynet is a sentient computer that defends itself if you try and turn it off, okay? That was the sort of the initial part of the plot, was they tried to shut it down, and it decided it didn't want to be shut down. And since it was in charge of the weapons systems of America, it fought back, right? There's a guy called Connor who kills it eventually. And then there's Terminator who's sent back in time to kill Connor and a bunch of stuff like that, right? So those are the basic, that's the plot. And it was a hack, so these are the hackers. So we have a Cassandra cluster that detects it's being attacked and responds. We have a Connor monkey that kills Skynet nodes, and we have a Terminator monkey that kills the Connor monkey nodes, right? And there's Skynet, there's the counter guy, and there's the terminator guy. So how are we going to implement this? Well, we're going to have Skynet store a history of its world. Everything it ever sees, it'll just log into a memory list. And then it will have like a brain that has actions. And the action, like if it loses a node, it will obviously replace that node. But it said, you know, if I'm losing nodes, I should get bigger so I have more nodes to start with. So the reaction to start to killing off a Skynet cluster is it gets bigger and bigger and bigger the more you try and kill it, right? Also, if it's being targeted in one zone, it should be able to replicate itself to another zone and another region. And so this cluster and then split so that there's now replicas of this Skynet cluster sort of floating around in Amazon, sort of lurking in different places and trying to hide. And also, if it sees a Connor monkey, it starts up a Terminator monkey to go shoot that Connor monkey, right? So the implementation plan here was in Priam. We already have auto-replacing missing nodes. We know how to grow the cluster. We actually need to figure out how to replicate to a new zone, but that's actually pretty simple code, and move to a new region. We've got some automation there, but it's not quite done yet. So there's a little bit of new code there. We have a couple of key spaces, actions and memory, and then maybe a cron job once a minute that just reads actions and runs whatever's there, right? Another interesting thing is if you split this off and you actually successfully kill some of the nodes, it would actually forget things, right? If the only parts of this key space were in a certain node, it would forget. But if it ran into another copy of itself, they could merge and they could repair each other's memory. So you could have a self-repairing, self-learning. So that means I can inject a new action into one Cassandra Skynet node, and as it ran around, it would infect all of the other nodes with that new action. And then the Chaos Monkey is pretty obvious. So here's my simulation. This is US East with 4 Skynets running in it. There's Connor Monkey, who's popped up in Amazon, Brazil, because it was far enough away to draw the picture. He zaps Skynet and takes one out. Here's the Terminator Monkey, who obviously is in California, because that's where the Governator lives. And Skynet repairs itself, and then he goes and he takes out the... yeah, so it's a wonderful simulation, isn't it? Anyway, so I thought that would be amusing for everybody, but that's basically it. I'm done with the slides. I'll take some questions now. And as you can see, it's a good idea that good job we haven't actually implemented this yet. So the question is, do we anticipate problems with SSD wear out since we're write heavy? There's 2 things. One is our workload isn't write heavy. We have we have 50 different clusters. We have everything from almost 100% write to almost 100% read and everything in between. On the other side, what does SSD wear out mean when I'm renting them by the hour? I don't care. That's Amazon's problem. It's baked into the cost, right? If an SSD wears out, kill the node and get another one, right? You know, if I find that one of them, I might need to put some measurement in there once they get a bit older, that I could detect a bad one and just kill that node and keep replacing until I get good ones. But it's not the same model as Datacenter where you buy stuff and keep it for 3 years, right? I don't care about SSD wear out, basically. And the other thing actually with Cassandra, there's no write amplification in Cassandra's writes to disk. It's basically the perfect SSD workload. It does a single write, it's a big write, it's sequential, and it never writes it again. It never updates. So, and it's a big write. So, and then a bit later it does a merge and deletes that file. So it's a very clean interface, where if you put a B tree on top of an SSD, you're working it really hard and it will wear out much quicker. The standard Amazon instances have 2 to 4 disks, spinning Rust, and you can do, you know, they spin at like 100 hertz, right? So you get a few hundred IOPS. That's all you get. 2 disks, 2 spindles worth of capacity. On the other side, it's a stripe of a large number of SSDs. And SSDs, there's nothing spinning. I mean, even one SSD will do, cheap SSDs do 10 to 20,000 IOPS easily. And this is an array of small SSDs that have been abstracted up as a volume from Amazon's point of view. So SSDs, it's random read, it's flash, right? So we measured it. We got 100,000 reads, 100,000, you can do 100,000 IOPS, reads or writes. Depends, you know. The write patterns matter, but the Cassandra write pattern works really well. So yes, it is a rags to riches thing. I now instead of being constrained at a few hundred IOPS, I now have just a ridiculous number. Like I drove them to 3,000. Right? I have 100,000. I got as far as 3,000. Some of the worst we did so far, I think we got up to about 40,000 IOPS. After doing some particularly pathological stuff to one of our clusters, which was a bug. Right? But the system was just going, yeah, I can do that. Right. So the question is, if I'm sending a remote copy of the data, do I do anti-entropy on it? Well, Cassandra has several anti-entropy systems in it. So the first thing is hinted handoff. So as I mentioned, when I send data remotely, I hold the copy of that data locally until I've heard acknowledgement that it arrived. If I don't hear the acknowledgement, you know, after a long period of time, maybe this node crashes or something and you've lost it. But that covers short-term loss, right, for, you know, days even. We also, the two maintenance operations for Cassandra, and these maintenance operations are relatively I/O intensive. One is compaction, which compresses the SS tables into fewer bigger ones. And the other one is repair. So repair takes all the nodes and it builds Merkle trees of all the data that's in each node, and then it ships those around and then compares them. And on the regular disk-based nodes, it's painful because it overloads the nodes. And you get I/O shortages, and you get, you know, it affects your read performance when you're doing this. With the SSD ones, we have enough I/O bandwidth that we can run repairs and compactions without taking the nodes offline. We typically take a node offline to do compaction and repair on it. The trouble with repair is you're comparing all 3 copies of the data. So if you're trying to get good read bandwidth, you have 3 copies that are all busy. So there's a thing called staggered repair that tries to stagger the hard work, and it sort of helps a bit. It doesn't help completely. The real answer is to run on SSDs. Okay, right, thanks very much.